Okay, so vertical asymptotes, factor the numerator and denominator, look for common factors and reduce, and then you take whatever's left over in the denominator and set that equal to 0. So we'll go through an example or two like that today. We have a new term called end behavior asymptotes, and hopefully you're familiar with that end behavior. That's when we talked about the limit as we go to the far left or the far right of the graph. And all we have to do is compare the asymptotes. So the m to the n, well, notice what those are. If I compare the degrees, that's whatever the degree is in the numerator to the degree in the denominator, that will tell us the types of horizontal asymptotes if they exist. So if your top degree is smaller than the bottom, that means the bottom is moving faster. That's a y equals 0 asymptote. And again, we'll show you how this works as we move on. If the top degree is equal to the bottom degree, then we have a horizontal asymptote at whatever the coefficients are. And we'll see an example like that today as well. But the new part today is what happens if the degree is larger on top and smaller on bottom. Well, it's always told us that there was no horizontal asymptote. However, there is something that occurs when the degree on top is bigger than the degree on bottom. And that's slant asymptotes. And how does that tie into what we've been doing? Well, to figure out where the slant asymptotes occur, we do long division, which is just dividing the denominator into the numerator, and then we're going to ignore the remainder. And what's left over is the slant asymptote. I might even change the bottom part. I would prefer it to say slant asymptote here. Okay, so I'm going to give you guys a second to get caught up on that. And as you're writing down, I'll just talk to you about conferences last night. So I went through and I called 55, 60 parents last night. And I geared everybody that was at below a 70%. I made sure to contact their parents, and I either spoke with them in person or I left a message. I also sent an email out that had a video to every parent and every student. You guys hopefully got that through Schoology as well. But it was just a YouTube video that said, here's what you can expect in class, and this is what we have coming up, and this is what you can still do to improve your grade. So I just want to share with you all in person what I talked about. So one of the big things that came up, because I was talking to students that were below a 70%, and one of the big things was missing homework. So you can still turn in anything that's from this unit 2, and so the new material, get that turned in. But what I started to think of was students are struggling with this day-to-day routine of kind of getting the homework done and getting it submitted. And it made me think about, the difficulties that you face as a student. The first thing is we meet on Zoom. We don't meet face to face. And I can't tell you every day when I walk around and check homework, like, hey, you're missing this. When are you going to get this done? So we're missing that personal connection, which is a big piece. So I can't give you these daily reminders. But what I'm hoping is you're checking Campus, and that's our official gradebook, but you're also checking Schoology, and you notice that if there's anything that isn't submitted yet, then you need to get that turned in and make sure you're on top of it. The other thing that I noticed was a lot of our work is on Delta Math, and there was 3 or 4 students that had a lot done on Delta Math, but they didn't submit screenshots to Schoology. So if that's you, if you've done a lot of the Delta Math and it still says missing, reach out to me and let me know so I can give you the points and the scores for the Delta Math that you didn't submit to Schoology. And if you've got a lot that can't be submitted, or instead of going back and submitting 10 different assignments, screenshots into Schoology, meet me in my office hours and I can just look at your Delta Math and I'll match that up to the gradebook. And then I can see, oh yeah, you know what, you finished these, and we can communicate. If we don't communicate, then I don't know if you did finish it or didn't. And it's near impossible for me to go through. I have 157 students this year. It's almost impossible for me to go through and check each individual person in Delta Math for all my classes. So I just want you to know if that you think that you finished something, reach out to me and let me know. And it's best to do it in my Zoom office hours from 1 to 2. Okay, so one thing I'll show you here quick is a lot of conversations I had were about what can we do to get your shoot, I gotta find a what can we do to get your Unit 1 test score up, right? Now I told you before that we wanted that to be done by like early October is to do the remediation for Unit 1, and then we said we were gonna open it back up so students could get their um, after having a conversation with their parents, you know, it gives you an action to take. So I'm just kind of looking here. There we go. Sorry. All right, so here's Delta Math. Now this is a student viewpoint of Delta Math, and the optional factoring practice, that was something that was due a while ago, but it's open all year. So if you're not great at factoring, you can always go back and do that. But anyways, if you scroll through here, you can see this is just my account that these didn't go through. But if you scroll down in the late credit, no credit, there's one that says Chapter 1 Review Study Guide, also Chapter 1 Remediation Assignment. So if you click on that, there's a lot, right? You have to do one problem of each of these successfully. Now it says you have 3. You just have to do one successfully from each one. The reason why we put 3 is so you could just go through and keep doing more if you needed to. But if you do one from each of these and you email me the screenshot saying you're done, I will go back and change your grade to the Chapter 1 test to a 70%. All right. Now, I don't want this hanging over your head, so I would like this done by hopefully by Monday of next week. That would be ideal because then you're ready for the Unit 2 stuff and we can go from there. All right, so that's open to everybody. The Chapter 1 remediation assignment, if you scored below a 70% on that first test, go ahead and do that, and that'll boost your score up to 70%. Okay, so if you have other questions, you can come talk to me in my office hours. I sent a couple of people reminders that, hey, I spoke with your parents and I would like to invite you to my office hours today so we can talk about a plan for getting you caught up. So, all right, let's start with the learning today. We're going to jump kind of right into this. We have a little bit of a shortened hour because of the hybrid schedule at Tartan. And this is basically the title of the notes today is 2.3 Finding Asymptotes. You've probably seen this as a t-shirt before, but this is what we're learning is asymptotes are what a graph approaches, but in like a vertical asymptote, it will never cross this line as you go up or down on the function. Okay, so we're going to start with this. I would like you to write this one down, and we're going to go through those list of problems or asymptotes that we just found and make some sense to that first page of notes that we went through. All right, so, and then eventually we could actually create our own graph with this, and that's what these are. These are graphs that we're just going to use to confirm our findings. So really, it's all algebra today. All right, let's start off with X or vertical asymptotes. Now, there's something really important that we have to do with vertical asymptotes. In years past, vertical asymptotes are what makes the denominator equal to 0. Well, you can see that right away. So I could actually just do this. And I believe for this problem, we're going to be okay. Set the denominator equal to 0. And x equals 5. There's my vertical asymptote. Okay. However, in the notes that you guys took, we gave a little word of warning about we have to be conscious of what's happening in the numerator first, or as well. And I want to think of, can this be factored? So I'm thinking, are there factors of positive 3 that add up to negative 2? If so, we're going to try to factor the top and the bottom. Well, 3, the only factors of positive 3 are negative 1 and negative 3, or positive 1 and positive 3. And when I add those up, they don't give me the middle term. So that means that this top trinomial cannot be factored. So therefore, there are no factors on top that are going to reduce out with the x minus 5, which means there are no holes in this graph. All right, so here's my vertical asymptote. I know if I was to draw a graph at x equals 5, I would have a dotted line going vertically. So let's try horizontal. Now, there doesn't have to be vertical or horizontal asymptotes. We have to check, but it's not a guarantee that they're going to exist. So when we check the horizontal and vertical asymptotes, that's where we're comparing the degrees. So in your notes, we compare the top degree to the bottom degree. And notice that there isn't a coefficient, or excuse me, a degree right here. So technically, we can call that a 1. Well, in this case, what do we know? We know that the top degree, and again, you're really just looking at the beginning pieces here. And I'm going to tie a connection into limits here in a second. Because horizontal asymptotes are what's happening is you go to the far, far left and the far, far right. But what we're going to do is we're just going to compare the degrees. How does 2 compare to 1? Well, in this case, m is greater than n. So what is that going to look like? I'm just going to jump back really quick to our page so we can make a connection to the notes. So when m is greater than n, that means there are no horizontal asymptotes. However, we have to do something new, and this is the slant asymptote that we're talking about. So we're going to introduce this idea of a slant asymptote right away. So if there's no horizontal asymptote, then we're going to check the slant asymptote. And this is where long division comes in. Let me know if you guys have any questions. You can unmute yourself or type it in the chat and you can say, slow down. How did you get that? What are you doing? Because this is new material. Just remember you're on mute. So if you need to, you can unmute yourself. All right. So what do we need to do? We need to do long division just like we practiced the other day. And we're going to take the denominator and we're going to see how many times does the denominator go into the numerator. So hopefully this is the new, or this piece is what you're already comfortable with. And the only new part is the act of, we do this to find slant asymptotes. All right, so remember our goal is to take this x and make it look like the very first term, x squared. And the only way to do that is to multiply both pieces by x.
I just wanted to see you before I go. I'm not leaving yet.
What's that, Jacob?
Was I unmuted?
Yeah.
Sorry, my notebook is pressing down on my
Oh,
keyboard.
that's all right. That happens.
That's okay.
I just wanted to make sure I had answered your question if you had it. So, all right. So what do we got? We got x times x is x squared, x times -5. And then do remember when we say subtract, this is like adding the opposite. So we're basically subtracting both pieces here. And I like to, sorry, I want this to be out further. Oh boy. There we go. You guys are probably so sick of watching me mess around with this pen. Okay, so we subtract, but I think of it as adding the opposite. So everything inside changes opposite signs, and then we're just going to add, now that they're opposite signs, we're adding the opposites. So those go away. X squareds reduce out. And then I end up with 3x plus 3. This 3 just drops down. So then we have to do it again. And I want to multiply this x so it looks exactly like our new beginning term, which is +3. So I'm going to distribute 3 times x is 3x. 3 times -5 is -15. And then we're going to add the opposite. So we write subtract, but then just remember it's adding the opposite of all of these terms. And if we do it right, the first term should always add up to 0. And then we have 18 left over. So what do we know? Then we know we have our answer, x plus 3, and there's a remainder of 18. And the remainder always goes over whatever you're dividing by. So I'm going to throw in a little bit of, it's officially pre-calculus, but it's a big reason for calculus here as to why we get the answer that we do. Okay, so don't worry too much about what I'm going to do down here. What I want to do actually is take the limit, because we're looking at end behavior. We're looking at what's happening to the far left and the far right of our graph. Well, the end behavior has to do with limits. It has to do with going to positive infinity, or really, I might just put positive or negative. Because that's what we're looking for, is what's happening to this function as we go really, really far left and right. Well, the behavior of the graph is controlled by the two pieces. It's controlled by the red part, which was our answer, and the remainder. So watch what happens as we go to positive or negative infinity. And again, I put plus or minus because we could take either one and we're going to get roughly the same answer. Instead of putting f of x, we know what f of x is now equal to. Okay. Now I'll also say this. Here's the nice thing. Once I show you this, you'll kind of get an idea, and we don't ever have to show this work in pre-calculus. You will in calculus, but this part is just getting us to an understanding. So what happens if I take this answer and I go to x equals infinity? Well, what's going to happen is I'm going to take just the red part. You know, let's save a step. I don't need to write this part. I'm going to take just the red part and I'm going to plug in positive infinity in to both spots where I see an x. So what if I do positive infinity plus 3, that's this part, I plugged in infinity here, And then I'm going to plug an infinity into the bottom x right here. Now that's kind of weird, right? That's actually not easy for us to just simplify. But what I want to think about is the understanding. What's going to happen right here? Well, this part is going to turn into 18 over infinity minus 5 is still infinity. So then I want to think about, well, what is this part going to turn into? If 18 divided into an infinite amount of pieces, that's really equal to 0, which means this part is going to go away. And the same thing will be true if we head to negative infinity. So if I made this a negative infinity, this piece is going to be 18 divided by negative infinity, which is still 0, which tells me the only part that decides on where my graph is going is this piece right here. So that's the part that you really, I'm not sure if you guys fully grasp that. On a graph, you'll kind of see what's going on. But it's the x plus 3 that controls the behavior of the slant asymptote. So all of this work basically told me I get to ignore the remainder. Okay, so again, you don't have to, all this work right here, you don't have to really grasp that or do any of it. You're just looking at, when you get your answer, your slant asymptote is the x plus 3. It's not the remainder. We're going to ignore the remainder. So all you're doing is you're doing long division, and whatever your answer is, that's your slant asymptote.
Later on, do we go into the remainder as well?
No, not. We are not going to deal with this remainder as any other piece. The only thing the remainder does is it controls like the center part of the graph. But if we're dealing with the end behavior just deals with the far left and the far right. So that's why we kind of ignore this remainder. And we just say our slant asymptote is the line x equals 3. Okay? So I know what you're probably thinking right now. What in the world are we doing? And how does this even remotely connect to graphs? So let's actually look at what did we just find and how does that appear on a graph? So you don't have to write this part here. Yeah, so the slant asymptote is actually the equation. So notice the equation was x plus 3. So that is, oops, that should be yellow. That is my equation for the slant asymptote. Now a slant, think of the word slant. It means kind of going up left or right. And I'll show you why our slant equation is not just a number, it's an actual equation. Okay. All right, so let's take a look at this graph. What I did, and I'll scroll down in a second just so you can see this, is I graphed this function in Desmos. Now I do want you to look at something. If you were to grab your graphing calculator and you take the standard window 10 by 10, this is the view that you're going to see. Now notice, it looks like it only has one branch of the hyperbola. Well, anytime we have a rational function, it's going to create, unless there's something really crazy going on, it's going to have multiple pieces to it. So you have to be careful. Your graphing calculator might not show you this whole graph. So in that case, you would have to change your window and zoom out so you can see more of this graph. Well, let's confirm a couple pieces based off of this graph. All right, we have a vertical asymptote at x equals 5. So if I go over to x equals 5, you guys see that vertical asymptote right there? We just proved that algebraically. The horizontal asymptote. There is no horizontal asymptote because this graph appears to be going down and this graph appears to be going up. But what we do have is we have another type of slant asymptote. And I'm going to do this kind of carefully. there's an asymptote, meaning the graph follows this purple line pretty closely. Well, what is that purple line? That purple line is the equation y equals x plus 3. Notice I did my best. Actually, I'm going to scoot it down, but there's the y-intercept of plus 3. And then I just go up 1 over 1, up 1 over 1. Now, this doesn't give us a perfect picture. So what if I zoom out a lot more? It might be really tough to see, but I zoomed out quite a bit. This is the same function. And we have the same behaviors here. I'm going to make this a little thinner. So because I zoomed out, it's really difficult to see this vertical asymptote here at x equals 5. Difficult to get it placed perfectly, but there's our vertical asymptote. But what about this slant asymptote? Well, look at what happens when I zoom out. Doesn't that look to be almost perfect? That dotted line, which is our asymptote, is actually mirroring how the graph is behaving as we go to the far left and far right. So that's the steps we're going to take today, is to find the vertical asymptote. You're going to set the numerator equal to 0, denominator equal to 0, but you have to check for factors. We're going to check to see if there's a horizontal asymptote by comparing the degrees. If the top degree is bigger than the bottom, then we have to move to a slant asymptote. And our work is the long division. And then we know that the remainder does nothing to the graph because it basically turns into 0. So it's just what's left over, the x plus 3. Okay, I think you'll get more comfortable as we do a couple examples and you see how the slant asymptote appears. All right, let's try this one. And again, I always like to relate this back to a graph. And we might even try to sketch a graph and see if it matches nicely. So I would write this one down again. Directions say find all asymptotes. This one has a very unique result. That's why I definitely want you to write it down. So what do we do with the vertical asymptote? Well, we have to do two things first. We have to factor the top and the bottom. Well, the top, if I've got x squared minus x minus 2, what are the factors of negative 2 that add up to give me negative 1? X minus 2.
Positive 1 and negative 2.
You got it. Thank you. Positive 1 and negative 2. Right? If I was to FOIL this out, I would get the exact same thing. So I'm going to actually write this over here so you can see what is happening a little clearer. We're just changing the top. And then I have to factor the bottom. And that's the tricky one. There's only two terms here. But you'll notice both terms have something in common. So we can factor out a 3 and an x away from each piece. And if I do that, if I take a 3x away from 3x squared, then I'm left with an x. If I take a 3x away from 3x, there's still something there. There's a plus 1. Well, wait a minute. I have a common factor on top and on bottom. When the x plus 1s go away, if you have a common factor on top and on bottom, that's a hole in your graph. And we studied holes kind of when we were reading domain and range, but there's a hole at whatever makes this 0. So if I just solved this in my head, what makes this 0? at -1, there's a hole right there in our graph. It's not a vertical asymptote. So what's left over? I factored the top, I factored the bottom. Whatever's left over in the denominator, we're going to set equal to 0. And that will tell us where the vertical asymptotes are. So really quick, if we divide by 3, there's a vertical asymptote at x equals 0. Notice how you could get in trouble if you just factored the bottom and you set both of these equal to 0. You might think that there's a vertical asymptote at x equals -1, but because of the factor up top reducing out, that made a hole instead of a vertical asymptote. Okay, so when we look at vertical or horizontal asymptotes, we're comparing the degree. And I like to think of it kind of using that limit notation. I won't tie in limits. That I don't want to confuse you guys too much. But notice, if I just look at the leading degrees and the leading coefficients, I get x squared over 3x. Well, since those are the same, technically there's a 1 here. When your degree on top is the same as the degree on bottom, don't those just reduce out? And what's left over? 1/3. So, because m is equal to n, we just look at the coefficients, the leading coefficients, which means there's a horizontal asymptote at y equals 1/3. Okay, now there's a question on tonight's homework that basically says, explain why there is no slant asymptote. Well, let's look at that. Why is there no slant asymptote? How do we know right away that there's no slant asymptote? The degree on top is not bigger than the degree on bottom. Since if they're equal, then we know there's a horizontal asymptote at the coefficients. So I'm just going to throw this in here. There is no slant asymptote spelling is hard. There we go. If you want to use really appropriate math terms, you would say the degree of the numerator is not larger than the degree of the denominator. But so notice when you do have a horizontal asymptote, that means that the end behavior is already behaving in a way that we know is a horizontal asymptote, which means we do not have to check the slant asymptote. You won't have a horizontal asymptote and a slant asymptote at the same time unless it's a really crazy function. So let's check and see, what does this graph look like? And I have to be really careful. I had to take a picture of this on Desmos because originally the graph was just a whole line and it didn't have the hole until I hovered. You can see my cursor right there in the image, and I couldn't get a screenshot of that. But let's plug in what we know. Let's confirm it. There's a vertical asymptote at x equals 0. Here's x equals 0. You can see that dotted line going straight up and down. And you can see the graph approaching it from the left and the right. So we will never cross that. And then you can also see as I go to the far, far right, notice how we're plateauing out. And as I go to the far, far left, I'm also plateauing. That's my end behavior. And it's not going at a slant, it's actually going at a horizontal line right here at 1/3. This purple line is the equation 1/3. All right, so that's really what we're doing today. We're checking for vertical asymptotes, we're checking for horizontal asymptotes, and if they don't exist, then we're checking for slant asymptotes. Do remember, hopefully, the end behavior model that we had you guys work through. So let's say I'm looking at this graph. Well, what can I conclude? What happens as the limit as x goes to the right of the function? Well, you were able to answer this. As I go to the far, far, far right on my graph, what was happening? My equation was going towards 1/3. In calculus, this is how we define a horizontal asymptote. All right, well, what happens if I go the other way? The limit as x goes to negative infinity of our function, which is just saying what's happening as I go to the far, far, far left of my graph. Well, this graph is going to approach that same purple line at 1/3, which again is my definition for a horizontal asymptote. So don't forget about the end behavior notation with limits. All right, so now our goal is to show you some different types of things that don't work out, or that may work out or may not. And there's some tricky things to these, and that's the goal with today, is to introduce you to some of those tricks, but use the process of vertical, horizontal, and slant asymptotes. Okay. We've got a function. Now we have a bigger polynomial on top and just a binomial on bottom. So we have to think about, how do we find the vertical asymptotes? Well, really quickly, we could say we set the bottom equal to 0 and we solve. However, we do have to just confirm, can the top be factored? And you might remember this from Algebra 2. If I have 4 terms, that was my factor by grouping. I don't know if you want to write this down, because I'll tell you it's not going to work, but let me just show you. Remember how we group the first two and we say, okay, what do these two have in common? They have an x squared, and then they've got an x minus 2. So that's what would be left over if I took an x squared away from those. And then over here, the only thing I could officially pull out is a 1 from each one of those. But the only way a factor by grouping is going to work is if these two are a common factor that I can pull out. And since it doesn't factor by grouping, this numerator cannot factor. All right, and that's a good sign, is when it can't factor, that makes our vertical asymptote much easier. So I might just say, we checked, but the top can't be factored. So what do we do then? Take the denominator and set it equal to 0, and that will give us where this function is undefined. So this is really quick then. Add 1, divide by 2. You could probably do that in your head. If I add 1 and then divide by 2, I get x equals 1/2. Let's think about why that works. Why is that true? What if I put 1/2 right in here for x? What's 1/2 times 2? That's equal to 1. 1 minus 1 is 0. I can't divide by 0. This is the only number in the whole function that makes this an undefined answer. That's why we have a vertical asymptote at x equals 1/2. So now we're going to compare the degree on top to the degree on bottom, the horizontal asymptote. So the degree on top is 3, the degree on bottom is 1. So in my mind, I think of this, because 3 is greater than 1, that means m is greater than n, that's referring back to the degrees. This tells me that there is no horizontal asymptote. But if there's no horizontal asymptote, then we have to check slant asymptote. And the way we do that is long division. So we're going to take the denominator, and we're going to see how many times that goes into the numerator. So why don't you do that? Go ahead and take a second, and I'd like you to do the long division, and then remember our slant asymptote is just whatever our answer is, and we're going to ignore the remainder. Okay, so I'm going to get caught up to you guys. My goal is to make this 2x look like x to the third. Well, what do I multiply a 2 to make it look like a 1? It's 1/2. And then how does an x turn into x cubed? It's x squared. So we got some fractions here which are not super friendly, but that's okay. 1/2 times 2 is 1x to the third. And then 1/2 x squared times -1 is -1/2 x squared. And then we subtract this new binomial, which I like to think of it as add the opposite. Change that to add the opposite. And then the x to the thirds go away. Now we have to be careful here. I might do some side work because we're going to deal with some fractions. You could write negative 1.5, but that doesn't help us a ton when we're going to the next spot. So I might do some side work here and say, okay, what is negative 2 plus 1/2? And to add fractions, I need the same denominators. So I'm going to just multiply this by 2 top and bottom. And then I get negative 4 over 2 plus 1 over 2, and that's negative 3/2. So in calculus, we do a lot of work with fractions. It's really good to practice that right now, just to let you guys know. So what's going to happen is this will turn into negative 3/2 x squared, and then everything else will drop down. And then we got to basically do the same thing all over again. What do I multiply 2 by so it turns into a 3/2? And that's kind of weird, is 2 times something has to equal negative 3/2. So a fast way to figure out what that thing is you're multiplying by is to get rid of the 2 and multiply it by the reciprocal over here. So the thing we need to multiply by is negative 3/4. That's how we figured out what was going right here. And we're going to distribute that to both of those terms. But then this becomes negative 6/4, which is fine. You could write it that way, but 6/4 ends up being 3 over 2 anyways. And then negative 3/4 times negative 1 ends up being a positive 3/4 x. And then we subtract, which turns into add the opposite. And then those go away. Since I have 3/4 and technically there's a 1 here, I might call that 4 over 4 because 4 over 4 is just 1. But that just helps me say 4 minus 3 is 1/4 x to the first power. So a lot of kids look at this and think it's super scary just because of the fractions. And once you get really good at fractions, this becomes a much easier process. So then I've got one last thing I have to figure out, okay, what am I going to multiply 2 by so it turns into 1/4? And I might do the same work I did here. 2 times something has to equal 1/4. So instead of timesing by 2, I'm going to move the 2 over to the other side and figure out that something that I have to multiply 2 by needs to be 1/4 times 1/2, which is 1/8. So that's where the 1/8 came from. Okay. So then the last piece here is we're going to multiply both pieces by 1/8 times 2 is 2/8, but 2/8 is the same as 1/4, and 1/8 times minus 1 is negative 1. And then we're going to subtract, which is add the opposite. And then I'm going to think of this instead of minus 1, I'm going to think of it as 8 over 8. So then I get negative 8 plus 1 is negative 7/8. Ugly remainder, not super friendly problem, but this is just really good work with fractions. And we're going to ignore the remainder. And here's my slant asymptote. It's an equation. All right, so I'm going to show you these graphs. And those of you who had tartan, if you want to start packing up, but keep your eyes on the screen, Miss Dahl is going to go around and squirt the spray, and that spray has to sit for 5 minutes before you can wipe it off. So you guys can just kind of watch as I show you how this slant asymptote appears, but you don't have to write anything else on here. Okay, so long division is what gave us the slant asymptote equation. Let me just show you what that looks like. If I was to graph the original function, it looks like this. Now you can see there's a vertical asymptote right here at 1/2. You can see there's no horizontal asymptotes, but then there's something kind of interesting. Right here looks to be like this part of the graph is following a parabola. And that parabola is what we call the slant asymptote. And its equation is right here, the one that we found. So notice the equation was some type of parabola x squared. And that's what it looks like. What if I zoom really far out? So what if I zoom really far out? Notice this behavior of our graph. The slant asymptote that was a parabola here is also mimicked right here. You can see that the very far ends, as I go to the far left or the right, my graph is following this parabolic shape, which is our slant asymptote. Okay, so we didn't get to these two, which are fine. It's the same thing. It's just a little bit different unique things. Here's what we got today. There was no great homework on this anywhere. So what I did was I created a pair deck, which I can't find it right now. If you go to our folder, you're going to open up under our folder today. There's a pair deck link that's your homework. So you need to submit that. Your answers will be just written on there. It's kind of like a Google Doc slide. You just write on it. But you also have to submit your worked out solutions on a separate sheet of paper to the assignment. So I'll be able to see the pair deck as you work on it, but I want to see your handwritten work. I want to see the long division. I want to see how you put the asymptotes for vertical and horizontal. And then you're just going to post those. And as soon as I can find my Schoology site, I'll show you what that looks like. All right, so if you go to week 8, Friday, you click on the homework. Here's the pair deck slide. So it's just going to take you to a slide, and it's interactive. So you get to write your answers on here. You're going to answer, how you feeling today? And then you get to drag the dot. How's pre-calculus going? Click on the next slide. And then for this one, you got to draw. I'm not saying these are the answers. I'm just saying you get to interact with it. And you may have done this before. And then here, you have to show your work, and then you answer your whatever you think the answer is, you're going to type it in. All right? So there's no work that you can show on here. These are just the answers. But what I want you to do then is when you're done, you're going to submit your work right here. So here's how you access the homework. Here's where you submit your work. All right, I will be on my after school hours from 1 to 2 o'clock today. I invited a couple of you personally so we can just have a quick conversation about, hey, what do we need to do to get you caught up? All right, and if you need help with that, I can work through the math with you as well. That's all I have. I hope you have a great day. Happy Friday.